guys doing?
Good, how are you?
Beautiful.
Don't have your tests graded yet. Hopefully by Friday, have them graded. I think y'all were right about number 29, the one that was limiting reactant, after looking at it. So I'll probably just end up giving everybody credit for that one.
For which one?
The one that was number 29 that was on limiting reactants. Okay, what we're starting now is, see if you remember me telling you this. Of the types of compounds, there's ionic, valent, the four different types of compounds that exist throughout the universe. We actually studied ionic compounds a bit, naming and how you come up with the formula and everything. We talk almost nothing about covalent compounds, which is where we're going now, which is why I want to put this general roadmap back in front of you. Metallic compounds come up just a little bit in our reactions, but we don't really focus on their structure. In coordinate covalent, we don't talk about at all. And these we just sort of talk about. But just realize we focused a bit on ionic compounds. I didn't really say much about structure. And then covalent compounds is where we are now. Just as a better picture for ionic compounds, if I did for NaCl, what y'all would know of as the formula NaCl, one Na and one Cl. Na is +1, Cl is -1. That's what we use for the formula. The actual structure, we have Na here, so I'm going to put Cl there. And then Na again. And I could keep going as long as I alternate down and alternate across. And you can also picture another chlorine ion right in front of this sodium. And then right in front of that chlorine, another sodium. And right in front of that sodium, a chlorine, then sodium, chlorine. So really it's this three-dimensional array that you can just stretch out as far as you want in any direction. That's what an ionic compound is. This is a crystal lattice I've sort of drawn here, or a model for one. Ionic compounds tend to be crystalline. If you dumped out some NaCl on the table, you see those little grains. They're just huge arrays of the ions as they alternate. So what's bonding these together is the charge. Ionic, bonding. And that's the positive and negative charges being attracted to each other. That's literally what's causing the bonding. The bonding is different for covalent compounds. This is, as you might imagine, covalent bonding. And yeah, this is actually called metallic bonding, but we won't cover that. You might cover that a little bit in 1212, metallic bonding. So gone back to ionic a little bit to show you what the structure is. Here's what we would call the structure for covalent bonds, covalent compounds, and realize these are what we call molecules. So I'm going to show you a molecule now. I'll do water. There's an OH molecule. Like if you had a sample of NaCl, it's going to be basically like this. You can get one huge crystal of NaCl, but usually they break off in little grains. We have that structure. But if you had a sample of water, you wouldn't just have one water molecule, you'd have like a beaker of some. And what you would have is a whole bunch of this. In that beaker would be lots of little units like this. And they are separate from each other. They can swim around and move around each other. These aren't moving at all, they're all solid. It's not that you can't make these liquids or gases, but you have to heat them to extreme temperatures. The ionic bond is really, really strong. We don't talk about the bonds between the molecules. These are the bonds. O to H is the bond. There's the bond. And what I'm drawing in the line here is indicating the covalent bond. So over here, if you looked at everything and you counted up all the sodiums and you counted up all the chlorines, you'd find out that you've essentially got a 1-to-1 relationship, a 1-to-1 ratio. For every sodium there's a chlorine there. And it's similar if I had, let's say I had MgF2. F has a charge of -1, Mg has a charge of +2. That's why there's 2 of these. And you would still have something similar going on here. I won't try to draw it. You'll get into how these structures work in 1212. But picture Mg2 plus F minus F minus, Mg2 plus F minus F minus, Mg2 plus F minus F minus. And down here, let's say I did F minus, Mg2 plus, and still made an array that was like this. Then it's 1 to 2, 1 to 2. So really this formula is indicating a ratio of the 2 different types of ions that are there in the structure. But it's kind of hard to do just on a flat surface. You really need to see these 3-dimensionally to see how you can even out the units in a crystal. But you can sort of picture it like this. It's still 1 of these and 2 of these, and then 1 of these and 2 of these, 2 of those, and then 1 of those in a big array. So you can still have varying ratios. It doesn't have to be 1-to-1. But still, it's still going to be one of those huge crystals. So the formula we write is really the ratio of the non-metal to the metal, to the anion to the cation. The formulas we use in covalent compounds, that is molecules, we would just call this H2O, because now we're focusing on this little unit. You see what I mean? So where the formula comes from is a little bit different. But I want to talk about how we get these structures and what this actually is, the bond. So it's for the ionic compounds, it's positive, negative, being attracted. They stick to each other, they aggregate, and they make that crystal. When these are created, it's a different thing. And sort of to get there, I'll leave this OH up there. H2O. Valence electrons. Do you remember this? That word anyway? Those of you who took chemistry before? Valence electrons. So, if you look at a periodic table, I brought some of these. Y'all probably have to share it because I don't have enough. But just so I'm not having to constantly flip back and forth. I really don't have enough, so y'all are going to have to share a little bit. If you've got your periodic table, pull it out. Share. I'll share over here. Anybody else? I got a couple. Anybody? Very simple idea. Let me bring up for one thing, since we're talking about molecules, covalent compounds, those are made up of all nonmetals. So I'm really going to focus on the top right of the periodic table and hydrogen. But if I just jotted it down real quick, I would say, here are the atoms we need to focus on for this discussion of covalent compounds. There's hydrogen over on the top left. I guess I'll include boron. That and maybe silicon, but it didn't show up in too many things. Chlorine, argon, and I suppose compose bromine, iodine. I'll write down just to be complete, or just to be contiguous. It's really all these that are the non-metals, maybe selenium. I won't add it though. Selenium, I guess, I'll put here just to sort of make it symmetrical. But that's that top right corner of the periodic table. There's some metalloids kind of along here. But really, these are the ones we want to focus on, because now we're talking about molecules and covalent bonding. Rarely, these are exceptions to general rules, but very rarely some in the top left will do covalent bonding, but those are metals. But chemistry is really the science of here's the broad rule, and here's the exceptions. I tend to stay away from the exceptions for introductory classes. Valence electrons, okay. If I ask you how many valence electrons does carbon have, you would look at carbon, you'd put your finger on it, and you'd count to the left. 1, 2, 3, 4. Carbon has 4. Nitrogen has 5. If you count, you go 1, 2, 3, 4, 5. Oxygen has 6. If you counted to the left, you'd count to 6. Fluorine has 7. If you counted to the left, you'd count 7. And it's true of the ones just below it. Phosphorus is the same as nitrogen, it's 5. Silicon and selenium are the same as oxygen, it's 6. All of the halides in this column are 7. The noble gases have 8. Let me just do these across. I do sort of want to focus here, because what I say for these goes for the ones below it. But let me do, here's hydrogen. If you put your finger on hydrogen and counted to the left, how much would you count up to? 1. This has 1 valence. And then if I skip over to carbon, how many does it have? So carbon, nitrogen, oxygen, fluorine, and I suppose I'll include neon. Okay. Here's what you do to make what we call a Lewis structure of an atom. These are called Lewis dot structures sometimes they're called dot structures, sometimes they're called Lewis structures, sometimes they're called Lewis symbols when you do this. So don't get confused by the varying terminology. But you do this, start with carbon. Here's carbon, and here's the Lewis structure for carbon. It's got 4 valence electrons. So you do this, you go around, you go 1, 2, 3, 4. That's it, that's the Lewis structure for carbon. Watch what happens when I do nitrogen, because it's got 5. I'm going to go 1, 2, 3, 4, and once I come around and start pairing them there, that's 5. So that's the Lewis structure for nitrogen. Oxygen, you're going to count to 6. 1, 2, 3, 4, 5, 6. That's the Lewis structure for oxygen. Fluorine, you're going to count to 7, and you'll go 1, 2, 3, 4, 5, 6, 7. Lewis structure for fluorine, and I'll go ahead and do neon. This one's 8, so you're going to go all the way around and then pair all of them. 5, 6, 7, 8. So you always have a periodic table on a test. You can easily find the valence electron. You can easily do that, and this gives you a lot of information. One thing, I'm going to refer to the I think books overemphasize this too much, but it is useful. The octet rule is referring to the idea that all atoms try to get 8 electrons around. That's their tendency. Last week or the week before, if I ask you, what's the charge on nitrogen when it's an ion? -3. Electrons are negative. And in this state right here, nitrogen is neutral. The number of protons in its nucleus exactly balances all the electrons. It has electrons in the inner core. These are the valence electrons. Valence just means the ones on the outside. Sometimes, like the awning out front of a restaurant is called its valence. Have you ever heard that?
Yeah.
Another use of the term is valence laws related to your property, meaning you've got a property and your neighbor property starts right here. Valence is like the edge of your property, you're not allowed to build a house there because you can't be right up against there. You know what I'm saying? So the word valence just means the outside. These are on the very outside, these 5 electrons. Since they're on the outside, they govern how that atom is going to behave. That is how it's going to react. That is what it's going to stick to, what it's going to react to, what it's going to do. The reason this becomes -3, because it tries to fill up its octet, its 8 spots for electrons out here. It will pull in 3 more electrons, and there it's happy, it lights that. But now it's going to be -3. This is why we get the ion, the -3 ion. So I'm kind of going back to ionic compounds a little bit here. I'm going to stick to covalent compounds after this. If I ask you, but here it is neutral, and we're going to deal with neutral atoms now. If I asked you last week, what is the charge on oxygen when it's an ion? It gains 2 electrons to pair these 2 up. Then it gets its octet, but now it's going to be -2. Fluorine will be -1 because it's only got 1 spot for that extra electron. So when they're ions, they're filling up these extra spaces and fulfilling the octet rule. We tend to call these inert, the noble gases. It isn't strictly true. These do make covalent compounds sometimes. I don't think they ever make ions, but maybe I'm wrong. Maybe at extremely high temperatures or something exotic like that. But so I'm really lying saying that these never end up in compounds. They do a little bit, but those are exceptions. But since all the spots are filled in this octet, there's nowhere for electrons to go to get in there. So these don't ionize for very, very, maybe some weird exotic situation. But for the purpose of this class, just assume these won't become ions because they don't have a spot for that electron or any new electrons. Okay, enough about ionic compounds. Covalent compounds, I'll go back to water. Here is the Lewis structure for oxygen. I'll draw the Lewis structure for hydrogen here and here. Here's the key to covalent compounds or covalent bonding. The hydrogen is an exception to the octet rule. It's only ever going to have 2 electrons total. I'll come back to the ones that violate the octet rule. All of these outside the box violate this octet rule. So hydrogen can. So it's got its 1 electron. It wants another electron to pair. And these 2 want an electron to pair. And if these found themselves in vicinity of each other, what will happen is these 2 electrons will link up and pair like these have. These 2 will link up and pair. And that pair ends up being shared by both atoms. Completely different mechanism than positive-negative being pulled together. It's kind of a property of electrons that they're able to pair one-on-one with each other. That's covalent bonding. Co meaning the 2 electrons, valent meaning the valence electrons. Covalent bonding. So the key here is when you're dealing in molecules, when you're dealing in covalent compounds, you need to know how many bonds any particular atom has a tendency to form. That helps you figure out the structure of a molecule. Meaning if I said CF4, what do you think the structure of that is? To think about that structure, you first want to think about how many bonds does each atom make. So that's the other piece of information you get here. You can see into the charges for the ions here, what I just explained. You finish pairing up. Carbon will be -4, this will be -3, -2, -1, doesn't ionize because they can accept that electron and pair up. Another way you can get an electron is share it with another atom. So for covalent compounds, what this tells you is how many bonds they make. This electron wants to pair, this one wants to pair, this one wants to pair, this one wants to pair. That means carbon can make 4 bonds. And I should say covalent bonds. Nitrogen has 3 of these unpaired, so it wants to make 3 bonds. Oxygen has 2 unpaired, so it wants to make 2 bonds. Fluorine has 1 unpaired, so it tends to make 1 bond with another atom, and I'll say 0 bond. I'm going to start by it just to say it does do covalent bonding sometimes. But don't overthink that. It's kind of a rarity, but I have to use some of these noble gases for some of the examples later. So there you go. You've got a periodic table in hand. You can easily make these by counting in a circle until you run out of valence electrons. And then you can look at and see the unpaired electrons and go, okay, that's how many bonds this makes. And of course, everything down is the same. Like all of these will make 1 bond. All of these will make 2 bonds. These will make 3 bonds. Carbon will make 4. Boron, metalloid, gets involved in covalent bonding sometimes. Hydrogen can only make 1 bond because it's only got 1 electron. So that's the next key piece to think about. All right, that's what valence electrons are. Lewis structures are just a way of representing molecules. So, let me revisit water and just say, if I walked up and said H2O, what do you think the structure of that is? Your first thought could be like this. You would go oxygen. Oh, let me say something real quick. That's how I drew the Lewis structure for oxygen. It's perfectly 100% correct if you do that. And this is true of all of them. As long as it's got 2 pairs and 2 single electrons, that's the correct Lewis structure. It really doesn't matter where you put them. You could even do this and it'd still be correct. That's still correct. It's got 2 pairs and 2 single electrons. So that's correct for, I want the camera. That's why I brought out the periodic table, so I didn't have to keep going back and forth. I tend to draw them like this because I always just start at the top when I start counting, so they'll all end up like this. But that's correct too. As long as oxygen has 2 pairs and 2 non-pairs, it's a correct Lewis structure. If you had H2O and you were thinking about that and you're trying to decide what you think the structure is, you could start by putting this Lewis structure, and there's 2 hydrogens, and now you can look at it and think, how can I connect these together? So there is this sort of thinking you can do that's not this very formal way. The formal way to make these Lewis structures we'll go into, and they're useful for more complicated molecules, but many molecules you can just inspect them. I like to say this every semester. Have you ever heard of Tinker Toys? A lot of people nod. That was around even when I was a little kid. It's like you got a little wooden stick and you got a block that's got holes in it, and you put the stick in, and some holes have 6 around and some have 4, and you can just play with them and make things. Y'all know what I'm talking about, Tinker Toys? That's what this is like. This will connect to 2 things. These will connect to 1 thing. So you can kind of keep this Tinker Toy logic in mind when you do these. If I said, how do you think you're going to get this? A molecule that's this, 2 hydrogens and an oxygen. How do you think you're going to make it? We could start by thinking like this. Notice if you connected the 2 hydrogens together, then you would have, and there's no more bonding. These only make 1 bond. So there's no way you're going to get H2O if you connect these 2 together. Because that's it. That's all it's going to fit if you use these 2 hydrogens. So you throw this out, and then you go, okay, what if I connect the oxygen? And then you go, oh, this makes 2 bonds, and each of these makes 1? Oh, well, I guess the structure's going to be, pair those 2 and pair those 2, and you would be correct. That's the Lewis structure of H2O. Like I said, the molecules can get more complicated. There's violations of the octet rule. So there's a list we'll go through, things you do, but the first thing you need is kind of a general backbone. I think, I'll go ahead and do CF4. Carbon, it makes 4 bonds. and we have 4 of these, and maybe it's obvious, you can see where I'm going. I have 4 of these, and each one of them only makes 1 bond. And I have carbon, and it has the capability of making 4 bonds. You think with Tinker Toy logic, it's kind of obvious what the structure is, right? It's going to be 4 fluorines stuck to a central carbon. These extra electrons do matter, though. So you have to draw those in. There is the Lewis structure of CF4, carbon tetrafluoride. So that basic logic is still there, but it sort of gets obscured when we start going through these rules. Let me grab. Oh, I should say this. In some instances, going back to ionic compounds, if I did magnesium, it would have 2 valence electrons, and I would do that. Instead of gaining electrons, you know that these become positive instead of negative. Instead of gaining electrons, what these do is lose all their valence electrons, and then this would be Mg2+. So metals lose the valence electrons, they go away, and that's how they become charged positive. And the negative ones, I did explain this already. Let's do sulfur just to be different, but it's like oxygen. If I said, what's the charge on sulfur when it's an ion, you would look at the periodic table. You would count 2 to the left and say that it's -2, but that's just this. It becomes -2 because those pair up. So there is such thing as a Lewis structure for S2 negative. That's just the full octet. And there is such thing as Mg2+, but the Lewis structure of that is this. And I guess I should also say, when we're doing Lewis structures, we put brackets around it and then we indicate the charge. But that's kind of a minor point. I think all that's kind of obvious. So I should say that. So I think you can do those because they're just literally make these Lewis structures. The ones that really matter for this discussion are the non-metals, though. And not even the ions, because we're not talking about ions anymore, even though I can't stop from bringing them up. But it's these I want to get to where you're making a Lewis structure. Hydrogen, boron, carbon, nitrogen, oxygen, fluorine, and neon. Really, I want to focus on these instead of the metals. I'll just leave that there. So really this discussion comes down to just this handful of atoms. And these are the ones that do not violate the octet. These have the octet. The rest of them can violate. The ones smaller, let's say, lower atomic number than the ones in this box, those don't achieve 8, they have less than 8. The ones starting with phosphorus have larger atomic numbers. These can have more than 8. So maybe I should say that. These will have less than 8. And these can all of these can have more than 8. They sometimes do stick with the octet rule, but we call it an expanded octet for those. Okay, so let's look at some of these from the exercises. And And instead of using our tinker toy logic, I'll follow the formal rules. Oops. 5, 27.
I'll just jump.
Examples for making Lewis structures. So picture being given these molecules and it's up to you to come up with a Lewis structure. You. And I'm going to pop back into section 5.3. So this is a section on writing Lewis structures. It starts with rule number 1. These are the rules you follow to make your Lewis structures. Write the correct skeletal structure for the molecule. I'll show you what I mean for that. This is probably the trickiest part that makes people not want to do this at all. So I tend to just go ahead and give you what I call the backbone structure, what they call the skeletal structure, and then you pick it up at 2. But some of these problems I give you, you still have to figure it out, but they're kind of simple. You can read this, but the simple rule I give is if it starts with H, go to the next one, and that's going to be the central atom. This one doesn't start with H, so this one, what I mean by central atom is, let's say you're given this, and I say draw the Lewis structure. What you're going to need is just kind of a basic outline of the structure to begin with. Take that first atom, as long as it's not hydrogen, put it in the middle, and then whatever else you've got there, stick it to that central atom. Cl, it's Cl2, I guess I'll just be symmetrical and do this. That's what I would call the skeletal structure. I don't have electrons in there, there might be other bonds that'll show up, but that's what I would start with. This is what you wish you had. I will tend to give you these on the test, but work on these problems and follow that one rule. Whatever the first atom is, make that the central atom, and then make all the other atoms come off of it. The book gives you a little bit of a hint when it's not that simple in those questions. So try to do those, but when it comes to a test, I'd rather you just start with this. Okay, here's how you start. Assume you've got the skeletal structure. That's rule number 1. Rule number 2 tells you start with the skeletal structure. I call it the backbone a lot, so consider that a synonym. Number 2, add up all the valence electrons. Meaning, I've got sulfur, I've only got one of them. How many valence electrons does sulfur have? It's 6. So there's 6 valence electrons from that one sulfur. I also have chlorine, there's 2 of them. How many valence electrons for chlorine? That's 7. These are all 8, these are all 7, these are all 6, these are all 5. Carbon is 4. Boron is 3. Boron's a weird one. 1, 2, 3. Here's the Lewis structure for boron. It makes 3 bonds when it gets into covalent compound. And hydrogen is 1, it just looks like that. So chlorine, 2 times 7 is 14. I've got 6 from there. So I've got 20 total electrons. That's what this is saying. Add up all the electrons from all the atoms involved. All the valence electrons. So I'm starting with 20. The next rule, rule 3, an octet. Give all atoms octets starting with the terminal atoms. This is what I'd call the central atom. These are the terminal atoms. I mean, if I had another one here and something else here, then I would have 4 terminal atoms because there's no more molecule out here. That's the end of the molecule, the terminus of the molecule. So I've got 1 central atom and 2 terminal atoms. If you have any electrons left after doing this, then you start putting them on the central atom. And when I say add atoms, add them as pairs. When you have a complete Lewis structure, you should have all the electrons paired. There should be no single electrons anywhere. So I got my backbone. I've added these up. In order to make my backbone, I had to use 2 electrons here, 2 electrons here. Remember that these lines are representing paired electrons, 1 from sulfur and 1 from chlorine. So there's 2 electrons there and 2 electrons there. I had to use those just to make my backbone structure. So I'm going to subtract 2 from here that I've used. Now I'm down to 18. I've got to get 18 more on here. Starting with the terminal atoms, 2, 4, 6. I put 6 on there so that this would have an octet. This pair of electrons, the chlorine gets to claim both of them as its own, so it's happy now. It's got its octet. 2, 4, 6, 8, 10, 12. So I used 12 electrons to complete the octet for chlorine. So I have to subtract 12. I have 6 left. I got to put 6. There's another rule. Where did I get it? Yeah, I'll leave it at that for now. Notice sulfur has more. Which one?
10 valence electrons.
Huh?
For the sulfur because it has the sharing the.
Say again.
Does that have 10 valence electrons?
Yeah. 2, 4, 6, 8, 10. It can have an expanded octet. There's another step here I didn't need to get to today about formal charge.
What does that say if you have no left?
If you have any electrons left, then start adding them to the central atom.
Okay.
This is not a great example because I wasn't going to do formal charge today. If you've used up all your electrons and all the ones that follow the octet rule are satisfied, you can stop there, at least as much as I'm going to show you today. So for now, let's consider that. I think that is correct, though. I don't think you get a formal charge on that, but let me do pH 3, just to follow this process. There are more rules here. I think I'll get to one on them today. We'll get to more and more exotic situations. pH 3. For you to make that backbone structure, step 1, this is going to be your central atom, and you just go P, H, H, H. Here's your backbone. How many valence electrons does phosphorus have? one of them, and that brings 5. Hydrogen has how many valence electrons? There's 1, so there's 3, so I have a total of 8 electrons here. I used 2, 4, 6 in the process of making this molecule, so I have to subtract 6. Now I'm down to 2. Hydrogen doesn't get an octet. It gets, your book likes to call it a duet, but it just means it's got 2. So hydrogen's satisfied, it's got its 2 electrons. Hydrogen gets 2, I don't want to write it there. But hydrogen's satisfied, so I don't need to do any of this. Now I have 2 left over, I'm going to put them on the central atom. That's the Lewis structure for pH 3. But again, notice if you decided to use the Tinker Toy logic, it's really kind of obvious. Following this formal set of rules is really for the more complicated situations that we will eventually get to. So it's kind of obvious, those 3 atoms that only make 1 bond, and that one atom that only makes 3 bonds, there's really only one way to connect those together. That's the Lewis structure for phosphorus. These are the Lewis structures for hydrogen. It's pretty obvious what's going to pair for that one. NF3 will be the same. That's BR2. Let's do, okay. Let me look at those examples again real quick. Okay, let's do 31 and 32. Okay, I will get to those. Where's my cheat sheet? What if the formula I gave you was so that's one of the noble gases. I told you there are exceptions. So this is just one of the exceptions. It will make covalent bonds. If you had this, what you would do is put Xe in the middle and stick the fluorines off to the side. There's your backbone structure. You use Xe as the central atom and these as the terminal atoms. Next, we're going to add up how many valence electrons does Xe have? It's 8. There's 1 of them. That's 8. So that brings 8 valence electrons. Fluorine, there's 2 of them. How many valence electrons? 7. 8, 7, 6, 5, 4. 3 for boron, 1 for hydrogen. 14 plus 8 is at 22. Okay, 22 total electrons that I've got to put somewhere. Going to step 3, well, before I go to step 3, I should probably add subtract the backbone electrons. So 2 electrons there, 2 electrons there. I've got 4 in here already, so I have to subtract 4 that I've already used. That gets me to 18. Next step, I need to start putting valence electrons around the terminal atoms. To get an octet around fluorine, it's already got 2. These count towards fluorine. now that fluorine has 8, and now this fluorine has 8. So I used 2, 4, 6, 8, 10, 12. So I have 6 left. So now when you have some left, you start sticking them on the central atom. 2, 4, 6. And yes, Xe is in this group where you can have an expanded octet, where you can have more than 8. And that's where you would stop. Everything has its octet. The thing that can have an expanded octet ended up with an expanded octet. That means you're done. That's the Lewis structure for Xe-Ap2. Another way you get expanded octets is if you just follow rule 1 and 2, you'll have an expanded octet. For instance, there's such thing as PCl5. If you follow the rules, you go, that's the central atom, and these all come out from the central atom. 1, 2. That's already violating the octet rule for phosphorus. But it's in this group, so that's fine. But just following rule 1 and 2, you'll get here. Or just following rule 1, you get here. And phosphorus is already violating the octet rule, but that's okay. Well, let's go through this. I can't remember where some extra electrons end up on that phosphorus. But let's see. Phosphorus has how many? 5. There's 1 phosphorus times 5. There's 5 electrons from there. Cl, we have 5 of them times 7. Is that 35? So we have 40 total electrons to deal with. We've already used 2, 4, 6, 8, 10. So we're down to 30. We're going to fix the octets on the chlorines first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. No, that's going to do it. We're down to no more electrons, and that's going to be the structure. So I just did this one to point out that you can violate the octet rule right at the start by following those general rules. You make the first atom the central atom, and you radiate all the other atoms off of it. It's not always that simple, which is why I say I will tend to give you these backbone structures so you can at least get started. The book gives you hints on some other ones. All right. Let me kind of take a left turn here and show you. You took chemistry before, you know that these are single bonds, but there's such thing as double bonds and triple bonds. Let me show you how those arise. Example would be C2. Yeah, this would be C2 F2. All right. And you can look at this and go, those 2 carbons, those are together central. And then from there, radiate out what's left. But I realize this gets a little weird, but this is your central atom or atoms. So there they are at the central point, and there's the fluorines out there. If I just played Tinker Toys again, and I made the Lewis structure for fluorine, and I made the single one there, and I did the Lewis structure for fluorine, and I put the single electron there, carbon. That's the Lewis structure for carbon. You can kind of see how this is starting to come together. You can do this, you get that single bond, and you can do this, you get that single bond, but I've still got to do something with these. So I'm doing the Tinker Toy method now instead of this method. But I can swing this electron over here, and swing this electron over here and pair those. And then I can swing this electron over here and swing this electron over here and pair those, and there I've made a triple bond. That's the Lewis structure for C2F2. The Tinker-Toy method, not following this formal method. What about C2F4? If I was doing C2F4, I would radiate more fluorines from here, and I realize it's not that easy to look at a formula and get this backbone. So like I said, I tend to want you to have the backbone rather than trying to figure it out. But now, what if I did this? I just started with the Lewis structures. So this is where I started today. Lewis structures of atoms. There's all the Lewis structures. And again, I'm going to first think, pair that, pair that, pair those two, pair those two, pair those two, and I still have these left to pair. I'm just going to swing them around inside here and pair them. There's a double bond. That's the Lewis structure for C2F4. Just using the Tinker-Toy logic to put them together. Giving you a backbone to work with, you can kind of see how these arise. The double bonds and the triple bonds. How about HNO? I said that if it starts with hydrogen, go to the next atom N for your central atom. So we're going to use N for our central atom. Okay, but let's go back to Lewis structures. That's the Lewis structure for hydrogen. Here's the Lewis structure for nitrogen. Just doing the Tinker-Toy method, those can connect, those can connect. I'm almost there. I've still got these unpaired, but I swing this in, I swing this in, that. There's the Lewis structure for HNO. Oxygen has its octet, nitrogen has its octet. We end up with the same result if we follow those rules, but let me do that just for the practice. You would start like this, now doing the formal method. There's your skeletal structure, your backbone. Nitrogen has 7, oxygen has 6, hydrogen has 1, so we end up with 14. There's one of each, so 7 from nitrogen, 6 from oxygen, 1 from hydrogen. So we've got 14. We already used 2, 2, 4, so minus 4. I mean, we already used 4. So we're down to 10 left. Now we start on the outside and we start making octets. Hydrogen never gets an octet, it only ever needs a pair. To do the octet for oxygen, we'll go 1, 2, 3 pairs, that's 6. That leaves me 4 to put somewhere, and I can put do I count wrong? 2, 4 gets us to 10. 2, 4, 6, we get to 4. Well, of course I can do this. What did I do with 4? This is 5. I was going too fast. Nitrogen has 5, oxygen has 6. I better write these up here because I'm going to mess up. 4, this has 3. Okay, so this was 12, minus 4 is 8. 8 minus 6 is 2. So 2, 4, I subtracted 4, that got me 8. And then I went 2, 4, 6. Subtract 6, I have 2 left. I put those 2 there. I'm down to 0. Now I look up there and go, okay, did I take care of all the octets? This one has an octet, this one does not. And hydrogen is not going to have an octet anyway. So I'm just going to steal that pair of electrons. So it's still on oxygen, but now it's also on hydrogen, and that's where the double bond comes from. So that's kind of 2 sub-rules here. If you run out of electrons and all the octets aren't filled, then you start considering how can you make double bonds or triple bonds to complete the octet. How can I get... that was a double bond. What if I did... CH2. So I end up with that. Yeah, I'll come back to that next time. Because we'll do something called formal charge. All right, as far as examples go, y'all remind me about the video. When I leave it hanging. Okay, I want to do. You remember the polyatomic ions? So we talked about ionic compounds, and then I told you ionic compounds are made. Positive charges and negative charges attract to each other. The polyatomic ions are actually covalent compounds. They just have an imbalance of electrons that leaves the overall thing charged. This was in that list, cyanide. These tend to get tricky, and I'll do more of these next time. We talk about formal charges and resonance and stuff. But if I said, okay, CN, follow the formal system, there's really not a term, they're both terminal atoms, really. There's not a central atom. But you would start with a backbone like that, but now when you add up the electrons, you have 1 extra electron. So carbon brings 4 valence electrons, nitrogen brings 5, and then you add 1 more for this. If it was -2, I would put a 2 here. If it was -3, I'd put a 3 here. If you add those up, you get 10 electrons. So that's my point. Whatever this charge is, the negative charge, you're going to add that many extra electrons to this tally of electrons. You see that? So that's one key with these polyatomic ions. So it ends up being negative because there's a certain number of protons in the carbon, a certain number of protons in the nitrogen. You add those up, and then you look at all the electrons around the carbon and all the electrons around the nitrogen, and it turns out there's 1 more electron out there than there are protons, and that's what causes it to be negative. The overall thing kind of carries this negative charge. So if I follow the rules, I've used 2 to make my backbone. I've got 8 left. Now I got to make 2, 4, 6, 8 down to 0. There, am I done? Do I have a full octet everywhere? Well, I don't. Carbon's only got 4. It's got these 2 and these 2. Nitrogen's good, but carbon's only got 4. So I'm going to steal this pair. There, nitrogen still has 8. And now carbon is up to 6, but it doesn't have 8 yet. So I'm going to steal that pair and stick it there. Now they all have 8. Carbon has its octet, nitrogen has its octet. So there, a triple bond arose because we got down to these rules and we had to start playing around to get the octets to work. In terms of practice, I think all of these are straightforward and easy. In fact, I don't think, these are the ones that I gave you. I think this is 27 and 28. This book doesn't have enough good examples. I had to look up for some that violate the octet rule. 33. Let's do this is very similar. Into H2. Let's do C2H6. There's your central atoms, these two carbons. And now you want to go and now if I want to follow these rules, it's 4 for each carbon, so that's 8 electrons, and it's 1 for each hydrogen, so that's 8, 9, 10, 11, 12, 13, 14. 14 total electrons. I've used 2, 4, 6, 8, 10, 12, 14 to make this. The carbons have their octet, the hydrogens have their 2. And I'm done, it's that simple. If I had C2H4, this is going to make a double bond show up. So I make my backbone, and it was it 14 total? 8, 9, 10, 11, 12. Now we have 12 total. 1 for each hydrogen and 4 for each carbon. So 8 valence electrons from the 2 carbons, and then 4 more for the 4 hydrogens. 2, 4, 6, 8, 10. I've used 10 to make my backbone. Now I have to stick that last pair somewhere on the inside and put it on either carbon. It's going to come to the same result. There, now I've used all my electrons. Now I look at my structure and go, is there any problems left to solve? Problem left to solve here is this carbon does not have its octet. The hydrogens are satisfied with the 2 electrons they're going to get. This carbon has 8. This carbon still needs 2 more, so you fix that by using that pair, sticking it there. So C2H4 ends up with a double bond between the 2 carbons, if you follow the rules. And you would come to the same thing. I think I did this very one earlier, didn't I? Where if you just kind of use tinker toy logic, and you built the Lewis structures, and you went, okay, I'll pair that, I'll pair that, I'll pair that, I'll pair that, I'll pair that. And then those last 2, how am I going to make them pair? Well, I'm going to swing them into the inside and form that double bond. You end up with the same result. And then C2H2. We would start with a backbone structure like this. Clean that up some. Carbons in the middle, hydrogens radiating out from the middle. And this time, 4 from carbon, 4 from carbon. We've got 8 valence electrons, 9, 10. So now I've got 10 valence electrons, 2, 4, 6 to make the backbone. I have 4 left. Hydrogen's fine, so I need to put 4 somewhere. I'll do that. I could do this as well. Either way, I'm going to have a problem with the octets on the carbons. So let's say I did that. I'm going to borrow this pair to make a bond, then I'm going to borrow this pair to make a bond. You end up with a triple bond. The tinker toy logic. I think I did do this example earlier. But if you just made the Lewis structures and you went, okay, I'm going to pair that, I'm going to pair that, I'm going to pair that. Now you would swing these 2 in to make a bond and make these pair by swinging them in to make a bond. You do end up with the same result. So I don't want you to lose that tinker toy knowledge, intuition. when you're doing this. It's just once we get to the more complicated stuff, this ends up being a slightly better way to do it because there are some rules you can follow. You start running into, do I take a pair of electrons from here and make the bond, or do I take the electrons from here? Actually, I could do either way and I would solve the problem, and then you start deciding which one is better. So I'll get into those, I think, Friday, or next Monday. I wonder if I should, I think I will do polarity and electronegativity. Let me go back up here, 5.2. This thing about polarity ends up a very important thing for predicting properties of molecules. And that's kind of where we're going. It's kind of a capstone to what we're doing. But we'll do molecular shape in between. But electronegativity, it might be worth reading through those rules before we finish this out Monday. Lewis structures. But let me cover electronegativity and bond polarity. Let me just stick together a quick molecule here. Bond polarity. So hydrogen and carbon is sharing this pair of electrons. Same here, same here. Carbon and oxygen are sharing that pair of electrons, and this oxygen and hydrogen are sharing this pair of electrons. All right. Let me contrast that with this molecule. If I remember right, there weren't any good examples in the book for this. I'll double check that before we quit. But and again, carbon and hydrogen is sharing this pair, carbon and hydrogen sharing this pair. Okay. Electronegativity. I'm sure the definition's in the book, but it's always very wordy. I suppose I'll bring it up, but I guess that would be the way to state it. The ability of an atom to attract electrons to itself in a chemical bond. Think covalent bond. Get out of my way. Okay, just this first sentence under electronegativity on page 217. Electronegativity. But let me describe that while pointing to this. Carbon has a certain tendency to pull this pair of electrons towards itself. Hydrogen has a certain tendency to pull those electrons towards itself. And how strongly it does so, there's a quick way to know. This is one of the reasons I like this periodic table. If you look at your periodic table, this number down here in the bottom right that I've not said anything about yet, that's a measure of the strength of electronegativity. The measure of the strength of the atom to pull that pair of electrons towards itself in a covalent bond. That's a lot of words for a definition, but you get what I'm saying. Oxygen says 3.5, carbon says 2.5, oxygen says 3.5. I like doing EN for electronegativity, so I don't have to write that big long word. Carbon 2.5. What does it say for hydrogen? 2.1. Okay, that's everything in these molecules. Say this. Electronegativity difference between 0 and 0.4. Between this is essentially what's in this is table 5.1. We needed that before I went on. So put it like this. Hydrogen is pulling on these electrons with a strength of about 2.1. Carbon is pulling on that pair of electrons with a strength of about 2.5. Or let's just say absolute 2.5. So if you ask which one's winning the tug of war for that pair of electrons, carbon's winning by just a little bit. Do you see what I'm saying? The electrons are actually being pulled towards the carbon a little bit. And they're being pulled away from the hydrogen a little bit. If I wanted to compare carbon and oxygen, I would say carbon's pulling on a strength of about 2.5. Oxygen is pulling at a strength of about 3.5. So in that case, for this pair of electrons, oxygen's winning. It's got those electrons pulled towards itself just a little bit. You follow that? Just based on those numbers, and you don't have to memorize the numbers, I give them to you on the periodic table. But to be more specific, let's do what we call electronegativity difference, which is what I've got in this column here. Electronegativity difference. And you do this. You need to take the absolute value, and then you put the two in there. Say for carbon and hydrogen, I've got 2.1, and you do minus 2.5. 2.1 minus 2.5 will give you a negative 0.4, but it's absolute value, so you're just looking for 0.4. And then let's do hydrogen, carbon bond. Let's do carbon to oxygen bond next. Okay, absolute value. So carbon is 2.5 minus 3.5. You could put 3.5 minus 2.5. I just throw them in there willy-nilly, but the absolute value keeps the negative from showing up. 1.0. And there is a carbon-to-carbon bond here, but you can imagine you're going to do 2.5 minus 2.5. Carbon-to-carbon is just going to be 0. Because both of them are pulling the same exact strength. 2.5 minus 2.5 is going to give you 0 for an electronegativity difference. That's the electronegativity difference. This is the electronegativity difference. So what can you say here? If the electronegativity difference is 0.4 or lower, I'd say between 0 and 0.4, then we consider it to be nonpolar. It is a tiny amount polar, meaning one of them is winning the tug of war against the other. So it's a tiny bit, but it's not enough to affect any properties. So in chemistry, we just say if it's that weak or weaker, we consider that nonpolar. That's what this is, nonpolar.
Are you gonna give them a chart?
I won't give them this chart, but I will give them the periodic table with the electronegativities on it.
Okay.
So what I'm saying here is, well, let me just put it this way. Everything's neutral here. There's no winner of the tug of war between any of these. And the same with carbon, that's 0. So these are being equally shared, and these are being effectively equally shared. Just because we follow this rule, because that weak of polarity doesn't tend to affect any properties, which we'll talk about how this affects properties. But those don't affect any properties. So can this just say, okay, 0.4 and less, we'll just say it's nonpolar. This will end up being polar though. Carbon to oxygen bond, once you calculate this out, now you're in between here. That's what we call a polar bond. This, erase these. This is a polar bond. Right there. I'm trying to show it thicker on the right side to say that the electrons are being pulled towards that oxygen. If the electrons are being pulled in that direction, what that means is we have a slight negative charge over here and a slight positive charge over here. They're slight, they're not a full charge like we would say an ion is. But it's just a slight bit of negative charge ends up over here around the oxygen, and that forces a slight bit of positive charge to be over here on the left next to the carbon. Does that make sense? Based on this tug of war sharing electrons? We would say they're not sharing them equally. The oxygen is winning, so it ends up with a little bit of negative charge on it because electrons are negative. We follow that? And those can cause attractions, and that's the point for going forward for properties. The fact that there's a slight positive charge here and a slight negative charge here affects the properties of the molecule. There's one I've left off here. Oxygen to hydrogen. I haven't done that one. Oxygen to hydrogen. So absolute value, oxygen is 3.5, hydrogen is 2.1. What's the difference there? 1.4. That's the electronegativity difference between oxygen and hydrogen, 1.4. So it's still in this range, so it is polar as well. And I'm going to say slightly negative here, although really you just put one negative there because it's negative either way. In this case, oxygen's winning again against the hydrogen. This was an electronegativity difference of 1.0. This was a difference of 1.4. So this is even slightly more polar. This positive charge is a little bit more positive than this positive charge because it's 1.4. It's more of an imbalance. So what we would say is that's a polar bond and that's a polar bond. Some books are careful to say polar covalent bond because we're not talking ionic bonds here. But there's your polarity. Follow that? If I stopped there, you would fully understand polarity. What screws people up with polarity is it has something to do with the shape of the molecule. I won't go into this much until we do molecular shape, which we will probably get to by next Wednesday, maybe next Monday. But let me give you an example. I think I better just use boron here to keep things simple. If I had boron, I need to make this symmetrical. So I mean for this to be 120, 120, 120, make 360. So think of that as a perfectly symmetrical, flat molecule. All right. Boron has an electronegativity of 2.0. So boron, if you look in the bottom right for boron, it's 2.0. electronegativity of 0.1. Is the H to B bond polar?
No.
0.1 is down in this range. So we go, okay, not polar. If I did fluorine, so if there's no polar bonds, then there can be no polarity for the molecule. The molecule has its own polarity, but if there's no polar bonds anywhere, then the molecule can't be polar. That's the twist, molecular polarity versus bond polarity. Okay, now if we do fluorine, fluorine is, oh, that was 2.1, no. 2.0 for hydrogen. 2.0 for boron, and 4.0 for fluorine. So we end up with and I'll point out 0.4, even a tiny bit more than 0.4, then you're in here. And then you get to 2.0, and then anything more than 2.0, then you're in here, larger than 2.0. So we're still just barely in the polar range. These are a little bit fuzzier than books pretend, but this is just a rule we go by. But 2.0 for fluorine, this is extremely polar. Oh, I didn't say this before, so let me say it now. So we're really getting, how do I do this? I shouldn't be using a wedge because that means something else. Let me do the negative here, positive here, negative here, negative here. The reason I know, and I should have said this when I first drew this one, the reason I know that the negative is over here and the positive is over here is because fluorine is more electronegative than boron. So the one that's more electronegative is the one winning, pulling electrons towards it. So that's why the negative goes on the side with the larger electronegativity. So you could look at this molecule and go, it has polar bonds. These are very polar. Boron to fluorine is a very polar bond. And then you ask, is the molecule overall, is it polar? And that's the weird thing. We sometimes represent these with arrows, like this. And the head of the arrow goes towards the negative side, and this side of the arrow gets sort of a plus sign on it. So if I drew all these arrows, and you're not crazy for thinking this is a nebulous concept, but those arrows are basically vectors. They have a direction and a magnitude, and the length of this little arrow indicates its magnitude. And if you add those three vectors, they add to 0. It's not obvious, but what I tell you to do is think of it as symmetry. I told you this is flat, and I told you it's 120 degrees, 120 degrees. So these are angle here, angle here, angle here, all equal to each other, so it's perfectly symmetrical. If it has that perfect symmetry, if these were non-polar, you could stop there. If all those bonds were non-polar, you could go, A, there's no polar bonds, and B, the molecule is not polar. Because polarity of the molecule comes from polarity of bonds, and if there's no polar bonds, there can be no polarity in the molecule. Here's a molecule with polarity kind of all over it, but because it's so symmetrical, all those, what we call dipoles, another word for this polarity is, this is a dipole. There are 3 dipoles here. Dipole just means di, there's 2 ends to it. That's just vocabulary. I'll use that word sometimes. And I managed to teach this class one summer and never used the word dipole. And then when I wrote the test, I used dipole everywhere. Everybody's like, what is a dipole? And I was like, I never said dipole. But that's also called a dipole. It's got a negative side and a positive side. That's a dipole. The polarity in the bond is a dipole. But those all cancel with each other because of the symmetry. If you actually mathematically added those vectors, it would come to 0, meaning there would be no polarity. But we don't teach y'all how to add vectors, so that's part of the reason this is confusing. I told you guys I don't make you guys balance equations because you're iterating, and that's just, it's a weirder process than we even tell you. You would need matrix algebra to solve those analytically. So if you've ever tried to balance equations, you start with a number and you work through, and then it gets weird and you can't solve it, so you have to start all over. And you iterate through, and then it gets frustrating. The reason it's frustrating is we didn't show you how the math works. But the math uses matrix algebra, and we're not going to go into matrix algebra just to teach you the balanced equation, so I just kind of skip it. Same here, there's a way to add vectors. It's a fancy physics, mathematical trick. But I tell you, just think about it as symmetry. This is perfectly symmetrical. So all of those dipoles, all of those vectors cancel. So this molecule is not polar. It won't behave as if it's polar. And I'll tell you what the behavior is later after we do molecular shape. But let me switch this up a little bit. Let's say it was this, and we've already gone through that. That's essentially non-polar. We came up with, what did we come up with? 0.1 for this, and we go, okay, 0.1, that's in this range, not polar. So there's no polarity there. But now the symmetry's broken. It's not symmetrical anymore. And I'll show you, if you added mathematically, which is, we're not teaching you how to do that, but that's a dipole that indicates a dipole across this bond. That's a dipole that indicates a dipole across this bond. If you add those two dipoles together, you would get an arrow that's kind of, I guess I would do it like that. If you add those together, that's the leftover dipole. If you added them together with a fluorine here, you wouldn't have a dipole. But if you add these two dipoles together, you end up with this overall dipole, and now you've got this negative side and this positive side, and that will affect the properties because you've broken the symmetry now. Like I said, you followed everything I said, and now you hate it because of this. So if you can add this last little piece, then you understand polarity and molecular polarity and non-polarity. If it has no polar bonds at all, the molecule can't be polar. If it does have polar bonds, you have to think about symmetry to decide whether it's polar or not, the molecule. If it's perfectly symmetrical with these arrows, if it's perfectly symmetrical, then it won't be polar. They all cancel each other. But if it's not symmetrical, you do end up with an overall dipole for the molecule, and therefore this molecule is polar. I would say it like this. H. That's what I would say about this one. This one, let me get this big vector out of our face. This, I would say, yes, there are polar bonds. Is it a polar molecule? And then the last case was this one where we had some H, let me break it up a little bit, H, H, F. That's not symmetrical because you're going to have this, and these aren't polar. So this one I would say, yes, there are polar bonds. Actually, let me say this. If there is only one polar bond on the molecule, there's nothing there to cancel it out, so it's going to be a polar molecule. If there's one polar bond and only one, then there will be polarity for the molecule. That's only true for small-ish molecules. I think you'll do organic chemistry in 1212, and you'll talk about if the molecule is large enough that one bond doesn't make it polar, but pretend I didn't say that. I just can't help myself. We're always going to be dealing with small molecules, so if there's only one polar bond, there's no other polar bond that's going to cancel it. So if there's one polar bond, it will be a polar molecule. If there's two or more, you have to look at the symmetry. So that's why I wanted to change this back to F. Yes, there are polar bonds. But they're not symmetrical. So the molecule is polar. Those are the three cases to think about. If you have polar bonds and it's symmetrical, yeah, there's polarity in the bonds, but the overall molecule is not polar because that symmetry makes it all cancel. This does not have that symmetry, so the polarity of the bonds survives because it can't be canceled out. So this will be a polar molecule. This one not polar at all because there was no polarity to begin with.
What if they still cancel out though? Like the two?
You're saying wouldn't these cancel out? That's a lesson in adding vectors. No, they don't. This one tends to the left a little bit and tends down a little bit. This one tends up a little bit, but tends to the left a little bit. So you're left with something. But if you had this vector and this vector and this vector, that perfect symmetry just makes it cancel.
Okay.
I chose to use three things. If I did it with just two things, it's a little more obvious. How could I do this? It won't lead confusion. No, can't do that. I'm going to have to use a metal. I told you there's exceptions to things I teach you. Let me do beryllium. I know it's a metal, but just pretend everything's still kosher. These are like rare cases. If I did the full Lewis structure, I'd have to do that. But let me move the dots out of the way. We do sometimes represent molecules without the electrons because chemists know where the electrons are. But just always do Lewis structures because that's the lesson for you guys. But if you had this, there's no electrons around here. It's just these and these. And it's perfectly linear across. Are those going to be polar bonds? 1.5 and chlorine is 3. Yeah, I'm going to get a difference of 1.5, so that'll be in the range. Okay, so the electronegativity difference here is 1.5, so we're in this range. Chlorine is more electronegative than beryllium, so negative charge will be over here, positive charge, negative charge. So there is a vector doing this. And that makes it a little more obvious if they'll cancel. Do you see what I mean? But if I went, oh, wait a minute, no, that's just hydrogen. There's no polarity there. Nothing there to cancel this. So this ends up lopsided, and this will be polar. So maybe it's a little more obvious when I don't use three in three different directions. And when we talk about the tetrahedral shape, it's the same thing, but we have to think about that in 3 dimensions. Something linear like this fits on the board. Something that's flat and triangular like this fits on the board. Tetrahedral is 3-dimensional. I can't do it on the board. I mean, I can sort of do it on the board, but we'll get to that later. That's molecular shape. Y'all remember molecular shape? What I mean is, do you remember the word molecular shape? I know you don't remember it all, and I know you're sitting there going, I remember it. I remember I hated it. That's what you're thinking. But we'll get to that soon, and hopefully you'll grasp it when I explain it. So polarity and electronegativity. Let me see if there's any exercises that are. Seems like I look at this, and all it ever does is ask you if it's a polar molecule, and there's no calculating electronegativity differences. So I have to find some good questions on that. Vesper theory is where we're going. Molecular shape and polarity. So they stick those together. They don't do polarity by itself. So I will come up with some questions like this. But the questions will be like, I'll give you the whole Lewis structure and I'll say, do you see any polar bonds? And then you have to do the electronegativity difference and use this rule. And then find if there are any polar bonds. So calculating electronegativity differences and then deciding whether the overall molecule is polar is another question I can ask. But this book doesn't ask the in-between easier things, but I think that's worth doing. Just having some questions that I could put on a test and ask you which of these bonds are polar. And you would use the electronegativity differences and these rules right here to decide whether it's polar. I'll stop there.
Can you put quizzes up on all of them again?
Yeah, I'll get around to making quizzes. For now, use these for practice, and I'll come up with some quiz questions that are